You finished chapter 3, so you've gotten good at evaluating properties, particularly things like delta U, delta H, change in enthalpy. Now we're going to get into chapter 4, which is dealing with open systems and the details about working with engineering problems for open systems. So let's go ahead and get started. Would like to give you a little roadmap of what's coming up in chapter 4. And then within this video, going to talk about the continuity equation, also known as conservation of mass. And so chapter 4 is also a fairly long chapter. And so I've got two slides that overview gives the roadmap of what we're going to cover in chapter 4. Of course, first we're going to look at conservation of mass, also known as the continuity equation. And then I'm going to show you some tricks on how to calculate the mass flow rate, the rate at which mass is flowing into or out of, or both of an open system. We're going to deal with a lot of problems related to steady state, steady flow, and introduce the idea of first law of thermodynamics for different categories of open systems. I'm going to carefully help you get through different statements of the first law, but it's all the same fundamental. It's a statement of conservation of energy, very similar, but not exactly like the first law of thermodynamics for a closed system. And so what I've done is I've classified this material as both easy and hard. There's going to be some parts of this chapter that are easy. They're consistent with your Common Sense 101, with your previous experience so far. There's going to be other parts, I'm going to openly say, that they're tough, and you're going to have to work very hard to master these new concepts and work on your homework to get better and better at problem solving and quantifying the type of things you're seeking. So as we work through chapter 4 and introduce the first law for an open system, that's going to be the fundamentals, along with the continuity equation, conservation of mass. We're going to cover a lot of engineering details associated with this laundry list of engineering applications. And this is where, at least in my world, the material, the course, it really gets even more interesting, because you may recognize some of the items on this list. Something on this list might be your interest area, something you're interested in, or something you've wondered about, or something you've been exposed to in an internship or co-op experience. So I'm not going to read off that laundry list to you, but I'm hoping to get you interested in some topics that you've got some interest in already. Okay, so let's compare what's an open system and what's a closed system. Chapter 4 is going to be dealing with open systems, so I've tried to give some screenshots of some examples. So let's X out closed systems. And so you've got some experience now. The old piston and cylinder, that's clearly closed system. That's not chapter 4. The propane canister, propane bottle full of phase change propane, but it's a fixed mass. Not chapter 4. So here's some examples of equipment that you're going to be studying or being able to analyze in chapter 4. This is a cutaway view of a steam turbine. This is a cutaway view of what's called a gas turbine engine. It involves a number of different engineering components, but this is a stationary gas turbine engine that drives an electric generator. Well, here's just a plain old box fan. You're going to get some skills to where you could analyze a box fan if you need to. Here is a classic centrifugal pump designed for pumping water or other liquids from point A to point B. So you get the idea of the difference between an open system. What makes up an open system? How can I tell all these sketches are open systems? Well, I can tell because I see that each one of these is going to involve mass flows in and out of whatever I describe the control surface to be. If I put a dashed line around the equipment as a volume, a controlled volume, you'll see that mass is flowing in, mass is flowing out. That's what makes it an open system. Okay, now we're going to get down and we're going to look at conservation of mass first. So here's an open system, also known as a control volume or control surface analysis. You recognize this as it's just a barrel sitting out there. And I see I've depicted this as having three inflows. So there's three flows going in. I've got three flows going out. I've got the dimensions of the barrel, and at least right now in the screenshot, the barrel is partially full of water. Okay, and it's L high. Okay, barrel diameter D. All right. First little quiz. Let's do a mental quiz of something you already know how to do. So for this snapshot, how would you determine the mass of the control volume? So M sub CV. So you see, I've put a dashed line. The dashed sort of circle line, I should have made it red, but anyway, the dashed line, that's my control surface. And certainly you see that it's an open system. I've got three inflows, three outflows. How would you determine the mass of the water inside this barrel? How would you do that? Pretty easy so far, right? With your experience, it's simply going to be the volume of a cylinder. It's going to be pi over 4d squared times L. That's going to be the volume. Let's see, how would I get the specific volume? I need the mass times the specific volume. I'd get this, I see it's 25 degrees C. It's water. I'd go to my temperature table. In the steam tables, I'd look up V sub F at 25 degrees C, write that number down and do the math. The mass is the volume times the specific volume. So, okay, so that would be kind of like your quiz. All right, so moving along. Let's imagine in this screenshot that flow number one is big. It's a lot of gallons per minute. And the 2 and I are 0. They're shut off. And down here at low, and it says flow number 3 is a small number. It's only a couple of gallons per minute, maybe dribbling out, right? And 4 and E, they're shut off, no flow. So what do you figure is happening with that situation? Big flow coming in, dribbling coming out. What's happening to L? Now, the tank's starting to fill up, isn't it? Big flow in, dribbling out. So for this open system, control volume, that would be transient flow because the liquid level is rising and rising and rising and rising. All right, great. You've got a feel for the conservation of mass. You've already then got a feel for the continuity equation. So after studying, I've got 3 inlets, 3 outlets, got a barrel. I can sort of measure the tank height. I have the ability to calculate the mass of the control volume, M sub CV. After thinking about all that, could you write down the continuity equation for any open system? Could you do that without without going to the textbook, without looking for a formula? Could you create that formula on your own? Could you come up with the governing equation? That's the fundamental. Could you come up with that governing equation on your own? I'll bet you could. All right, so let's do that. All right, and so we're going to plop it down. Let's remind ourselves, what's the continuity equation for a closed system from chapters 1 and 2? Closed system, the old piston and cylinder. A statement of the continuity equation for this piston and cylinder is that M1 equals M2. The mass is constant. So whatever state you go through, 1 to 2, the mass is constant. That's a statement of the continuity equation for closed system. Okay, for an open system, we just sort of eyeballed some barrel with inflows and outflows. I'm going to suggest that you could write down an equation that would look like this. dm dt of the control volume, dm dt, it's a rate of change, equals the sum of this m dot n. That makes mass flow rate n. That's what m dot, variable m dot, mass flow rate n. If you sum up all the flows going in and subtract out all the flows going out, That's a statement of the continuity equation. So let's look at a wordy description. That's it. So if you want to take a screenshot of this, you've got the textbook definition of the continuity equation for any open system. Check. All right, so let's look at what the words say. I've tried to depict in words. The left-hand side, dm dt of the control volume. It says the rate of change, d by dt, that's d by dt. That's the rate of change, d by dt, of m, the rate of change of the control volume's mass. Okay, so that's what that left-hand side, okay, equals or equal sign. Well, sum of the m dot n. I've got a dot, and I've in graphically, I've made the dot real big. Now you don't have to make your dots that big, but by golly, you need to have a dot over M because it's used to depict the sum. Let's come over here. The sum of the M dot I. So in the textbook, that's consistent with the book. I means in M dot mass sum of the mass flow rates in minus the sum of the mass flow rates leaving, exiting, E, exiting. In, I, exiting, E, some of the mass flows leaving. So that is a very clear and easy statement of the continuity equation for any open system. Okay. And so you see, okay, I'll leave it right there. Now we're going to simplify our continuity equation. Let's say we've got steady flow. Let's say we look at the flows going in, and for each of these arrows, the gallons per minute or cubic meters per second, for each one of these is staying constant, and ditto for what's leaving. So, okay, 3 gallons per minute, 4 gallons per minute, 5 gallons per minute, 6 gallons per minute. So 3, 4, 5, 6 gallons per minute. It's the same flows in at breakfast time as it is at lunchtime. In other words, things are flowing in steadily and things are flowing out steadily. So what happens to our general statement of continuity for an open system when we have steady flow? Well, it says, look, if everything's flowing in steadily, kind of like our bucket, our barrel, okay, if the inflows exactly match the outflows, do you see that the level of the bucket is staying constant, isn't it? So in other words, dm dt of the control volume is 0. That's steady flow. So d by dt of anything for steady flow, the time derivative of anything is 0 for steady flow. So left-hand side 0. So we're going to simplify our continuity equation. M dot I equals M dot E. My phone's ringing and I'm going to need to ignore my phone. So we're just going to let it ring. Okay, so here we go. It says the mass of the control volume stays constant in time. That means this left-hand side is 0. And the rate of change of the control volume's mass equals 0. That's the scientific expression for the left-hand side of 0. So remember, so a statement of steady state, steady flow. The masses flowing in equals the masses flowing exiting. So there's our statement of continuity for steady flow. Pretty simple. Okay. Now let's simplify again. Let's see what we had. It said the sum of all the mass flows going in equals the sum of all the mass flows going out. Let's simplify. Let's look at one inlet and one outlet. It's only one pipe going in and one pipe going out of our open system cloud. It can be anything. Okay. Okay, so there's our statement of the first of the continuity equation. And so all we got to do here is, well, what's the sum of the m dot n? It's m dot 1 and m dot exiting, m dot 2. And look, for problem solving in this class, when we have an open system, steady state, steady flow with only one inlet and one outlet, what we're going to do is we realize that m dot 1 equals m dot 2, and we're just going to call it m dot, mass flow rate, m dot. Okay. In the green text box, it says you're going to be working with lots and lots of problems like this for the rest of the course and beyond in your engineering practice. A very common situation to be analyzing. And so I've devoted a slide, a very simple slide to something. So I've labeled it, it's all about the dots. It's all about the dots. So this is incredible. I should have stamped this important, even though it's simple and easy to understand. If we've got an open system, okay, we got one flow, any number of flows in, any flow, you got to be sure to put the dot over top of the N. M. For an open system, you got to put a dot over the M, and that communicates to everybody looking at your work, and it reminds you that you've got an open system, a flowing system, open system. So you pronounce this variable m dot, mass flow rate. Let's compare it to a closed system. You've got m is a fixed mass. It's just m. There's no dot there, right? And you're going from state 1 to state 2, so you said m1 equals m2. If I went back to this steady state, steady flow open system, and look, what if I labeled it, there's 1 and there's 2. I did do that. Would you see that m dot 1 equals m dot 2 equals m dot? Now, I see so many students turn in homework problems where they just put m1 equals m2 for an open system, that they get killed on their homework when they're in my class, because that is not the right nomenclature. It's very poor engineering practice to just put m1 equals m2 for an open system. So it's all about the dots. Some numerical. So let's go and look at some numerical situations. So now back to not steady flow, or let's analyze an open system, whether it's steady flow or not. I'm having to move my my Zoom menu around, and I think I've got it here. Let's add up our inflows for this example problem. I've got 5 plus 2 plus 3. That's 10, 5, 6, 7, 8. Yeah, 10 kilograms per second going in. Let's look at the outlets. I got 4 and 3 and 3. That's 6 and 4. That's 10 going out. I've got my outflows exactly match my inflows. That's steady flow. So L, the height of the barrel, is staying constant. That's it. So the scientific expression is dm dt of the control volume is 0. I've got my level L is staying constant since my inflows exactly match the outflows. Okay, now let's example transient flow. I've changed my flows in and out. I've got 5 and 4 and 3. That's 12 kilograms per second going in, and 3 and 3 and 2, 8 kilograms per second going out. 12 in, 8 out. So as time goes by, my liquid level is rising, isn't it? So the scientific expression is dm dt of the control volume is greater than 0. The mass of the control volume is increasing in time. Time rate of change greater than 0. I hope you're getting this. I hope you're catching on to this. This is not trivial. It's easy to understand, but it is not trivial either. Okay. Okay, let's another transient flow example. Let's see, I've got 3 and 4 and 2. That's 9 kilograms per second coming in, and 5 and 3 and 3. 11 going out. So you can see what's happening. The liquid level is dropping. The water level is dropping. Scientific expression, dm dt of the control volume is less than 0. Transient flow. So you got a couple of situations for transient flow. Mass increasing in time or mass decreasing in time. Steady flow, mass is staying constant in time. Let's say you'd like a little live demo. And so about a year or so ago, I decided to, in my basement, I've got a bucket and I've got a pump down here in a bigger bucket. And I've pulled my video cam over, my webcam over, and I'm showing you physically what the continuity equation looks like with my little demo bucket, trying to show steady flow and transient flow. So let's see, thermodynamics fundamentals playlist, continuity equation demo. So we've reached the end of this intro and statement of continuity for any open system. Continuity equation is a statement of conservation of mass. For any system, dm dt of the control volume is the sum of the mass flows in minus the sum of the mass flows exiting. for steady state, steady flow. For open system, steady flow, the sum of the inflows exactly matches the sum of the outflows. And then my last remark, it's all about the dots. So please remember, it's all about the dots here for open systems. That's an important takeaway from this video. And let's see, next video is I'm going to show you, give you some tips on if the mass flow rates are not given. Let me back up a slide or two. Okay. If you're not given these mass flow rates, I'm going to show you, and the book shows you some tips on how to calculate, how to determine those mass flow rates, just for some basic measurements. Okay, I hope that helps show you where we're headed in Chapter 4. And also, all of a sudden, just in a few minutes, we've covered the very general state continuity equation for any open system. I hope that helps, and we'll look forward to seeing you on the next video after I check my phone and see who's calling and what I can do for them.